So we are going to start our next chapter, which is about evaluating the thermodynamic properties. Okay. So, by the way, we all know that in thermodynamics we need to look at different properties, and those properties include two types: extensive and intensive. And most of the time we would be interested in intensive properties, just like pressure, density, temperature. All of them are intensive properties. Okay. So before moving on to the discussion how to evaluate those properties and how can we take advantage of different experiments which have already been done by various scientists, I would define 2 or 3 terms, okay, and then we would see everything in their perspective. First of all, let's define the term phase. So it refers to a quantity of matter that is homogeneous throughout in both chemical composition and physical structure. Now looking at this, it means homogeneous. It means wherever you check that its properties remain the same, and chemical composition and physical state should also be the same. Just like there are 3 states of matter which we know as mechanical engineers. Obviously there are other ones like plasma, and I think someone has discovered another type, I don't remember the name, but yeah. So we have 3 commonly found out states where you can say you have solid, liquid and gas. So each of them describe phase. Okay, like for example, if I tell you that there are some vapors and some liquid inside a container, how many phases would be there? 2 phases would be there. Okay. Now for example, if you have 2 immiscible fluids are there which can't be mixed together, just like let's say petrol and water, what does that mean? You would have 2 phases. Okay, 2 phases. Why? Because you can't mix them together. So if you are able to mix them together, just like alcohol and water, you would say this has become 1 phase. Okay, so then there is something which is known as pure substance. It is one that is uniform and invariable in its chemical composition. Now for example, if you just look at water, if you have water inside a container and that water may have vapors or it may have some liquid as well, if you go to the vapor region If you find out the chemical composition, still it is H2O. Okay, if you move on to the liquid region, you can see that its chemical composition is what? H2O. So chemical composition remains the same. So it means water itself is a pure substance, right? So this is something which you need to understand. So I hope everything is clear about phase and pure substance. In pure substance, you can have different phases, but it should be the same chemical material. Its chemical composition should remain the same. If you go into the phase relates to the material state. That means solid, gas, or liquid. Now, how can we find out the properties? Now, whenever you talk about state, what do you mean by that? It is a subset of properties, right? So if you define a state, what is the temperature, density, pressure, energy, everything related to this point. You jump on to the next point, then you define another state, and that state includes all those kind of properties which you can measure. So before going for fixing out the state, let me tell you that most of the time we are interested in intensive properties. What are those properties? Temperature, pressure may be an intensive property. Then we may be interested in density or specific volume. Okay, so these are the properties where we are most of the time interested in. Now, before going to define the fixing state, remember one thing, that in engineering, what you do is, any performance of any system may seem to be dependent on many properties. Just like, for example, if you think that this property of this point, any point in space or any point in your system, it may depend on many properties, just like energy, internal energy, kinetic energy, potential energy, pressure, density, volume, whatever you call. But the point is, in any engineering system, in every subject, you would see that in the rest of your subjects as well, in fluid mechanics, in control systems, in dynamics, you would see that sometimes you need to see that few properties are independent and other properties are dependent on those properties. Like, for example, there would be 2, 3, 4 properties which are independent, and all the rest of the properties would be dependent on those 4 independent properties. Okay, so the problem is you have to fix those independent properties first. Okay, so it means most of the time those properties, when you jump onto dynamics and control, you would see that those properties are known as state variables. Okay, now similarly we would have those set of properties as states in thermodynamics as well. Remember, whenever you define state, it's a technical word. And what do you mean by state? That you are trying to describe the state, the situation of a system at any point by a set of independent properties. That's what it means. So if you try to fix the state, there are few principles in every field. Just like, for example, you may have a flavor of a theorem which is known as Buckingham Pi theorem in your fluid dynamics 2 course. Okay, you would see that how do you fix the state, or how do you look at the independent properties. This is just one example. Remember that you would see its application in your fluid mechanics course. Similarly, you would jump onto control systems or dynamics. You would see that there are certain states which are independent of each other, right? Now, what do you mean by independent of each other? It means that if you say x1 is a property, it can't be equal to 2x2 or 3x2. It can be equal to the derivative of x2, it can be equal to the integral of x2, but it can't be equal to like 2x2, 3x2 and things like that. In your linear algebra course, you might have heard about a word like linearly independent. Okay, so these things are related to each other. whenever you say x1 equals to x2, what does that mean? It is linearly independent. So if it is linearly independent, it is quite obvious that the things are going to be interdependent, right? So whenever we say that those properties are independent of each other, it means their relationship is not very simple. Okay, so my point is that I am going to describe a principle which is known as state principle for commonly used thermodynamic substances. Commonly used thermodynamic substances means we use water, we use steams most of the time in many systems, we use other gaseous systems or liquid systems. So generally those liquids or those substances are known as simple compressible systems. Those water and let's say some other combination of gases which are commonly found in there, they are known as simple compressible systems. Now I hope you understand the word compressible. What does that mean? I'm sorry, this is system. What does that mean? Compressible? Its density can change. Its density can change. Okay, so whenever you talk about compressibility of a gas, compressibility of a liquid, compressibility of a solid, although it is not that visible in case of liquid, but still you would have certain kind of and you can I think there is a property named as bulk modulus in your mechanics of materials course. You would see that it is somehow related with this, right, compressibility property. But anyways, you can see that all these things are interrelated. Okay, I'm just giving you few examples from your other subjects as well, so that you can have a flavor and you may be able to understand those terms in their broader perspective. So the compressibility means that the density can change. Okay, so let me define the state principle for those simple compressible systems. Generally, you define it as if the specification of the values for any two independent intensive thermodynamic properties will fix the values for all other intensive thermodynamic properties. Okay, that's what it means. That the state principle says that if you specify two intensive properties of a thermodynamic system, it is sufficient to have all the other related intensive thermodynamic properties. Okay, like for example, if I talk about temperature and pressure, for example, if you have temperature and pressure, you can measure all the other properties related to density, energy, enthalpy, internal energy, all other things can be measured. Okay, similarly, if you might have chosen like temperature and specific volume. By the way, specific volume is just the inverse of density. I hope you remember. Okay, so specific volume and temperature. So it means that pressure would be a function of what? Temperature and specific volume. This is what does that mean. So for example, if I say that I need to find out pressure as an intensive property and I have temperature and specific volume, so it means it would just be a function of these two things, like any other thing. Density, you can talk about internal energy, you can talk about enthalpy. So this is what does that mean. So it means state principle has done what? State principle has done what? Sorry, it has fixed the number of independent states. Remember that. It has fixed the number of independent states. So it means you just need to look at the dependence of all other properties on only two properties. Okay, so You can say your parametric space. Parametric, what does that mean, parametric space? That if you have like pressure, temperature, specific volume, internal energy, enthalpy, all other things are there. So this is basically, you can see, let's say there are 5 variables and every variable would have so many values, isn't it? So just look at the spectrum, just look at the combinations which can be made by those 5 properties. I mean, it can be a huge value, it can be a huge number. So what you have done is, out of that huge parametric space or combinations, what you have reduced, you have come up to only two independent properties. Okay, so that's what does that mean. Now this is quite interesting. We need to understand it very carefully. Just look at those lines. For example, you have specific volume. This is specific volume, small v, and this is temperature. I have taken this figure from this website. Now you can see that these two properties are your independent properties. It is what? Yeah, I mean it depends on you, but sometimes you have to perform the experiments to check the independence, right? There are some other techniques as well, just like I have told you one example, Buckingham pi theorem in your fluid mechanics course 2. You would see that most of the time it depends on the experience. You can't just straight away say that this is my independent property, this is not my independent property. You can't say that. So sometimes you have to use your experience, sometimes you have to use your knowledge, and sometimes you have to rely on the experiments. Okay, it is not that straightforward. But anyways, coming back to my point, just understand this thing very carefully. These two are independent properties in our case, and I say that pressure, which is being drawn on this vertical axis, this is just a function of specific volume and temperature. Now once I draw the dependence, once I draw pressure as a function of V and T, it comes out like this surface. Okay, it is just like a surface. I hope you understand that. For example, if you just consider pressure as a function of time, let's say pressure as a function of time, it would be a line, maybe it would be a line. But if you talk about pressure as a function of two variables, it should be what? A surface. It should be a surface, right? So it would be like this. Do you understand that? So just look, there are few lines. I mean, if you go by this red line, if you go along this red line, it looks like as if it is having a constant pressure value, isn't it? Constant pressure value. So at this constant pressure value, I just drew a line on this surface. Now what does that mean? It means that this red line is known as an isobar. Red line is known as an isobar. These are the terms. Remember that. You should understand these terms very carefully. Now if you look at a line, a curve on a plot which is specifying a constant pressure, which is a constant pressure line, it is something which is known as isobar. Similarly, just look at those blue lines. Just look at that blue line. On that blue line you have some temperature value which remains constant along this line, isn't it? Right? So this is something which is known as isotherm. Okay, remember that. So if you look at that blue line, it specifies all the pressure and specific volume properties or values at one temperature. Just look at this. What is the temperature at this point? Let's say it is having some specific value. It would have same specific value of temperature at all of those points, right? So this is something which is known as isotherm. Similarly, even in space, if you find out that all, let's say there are few hundred points where you have the same temperature, if you connect all those points, so that curve would be defining an isotherm. Remember that. Okay, so this yellow region defines single phase. Now what does that mean, single phase? That on this yellow region you may have solid, you may have liquid, or you may have vapors. It means at a combination of that specific pressure, specific volume and temperature, either you would have vapors, complete vapors, or you would have complete liquid, or you would have what? Complete solid. Okay. So for example, what does that mean? If I just choose one point here on this surface, this is the point. That means that this is a point where I have a value of P1, V1 and T1, and this specification defines an equilibrium point. All of the points on this surface defines what? Equilibrium points. Now what does that mean, equilibrium points? Without giving some external energy, you can't change the state of the system. This is something which is an easy understanding for equilibrium. Without doing something externally, you can't change the state of the system. So you can say, if you talk about this point, any point. So all the points defines what? Equilibrium states of one system. Now quite luckily, there is a similarity found in the natural composition or the natural behavior of all the thermodynamic systems. Like for example, if you look at this surface would remain the same. The overall shape of this surface would remain the same for all the thermodynamic properties, for all the thermodynamic substances. And it's quite interesting to see that even if you talk about a mixture of gases, you talk about water, you talk about any other thing, the surface of this, the shape of this surface would remain the same. And this is known as PVT surface. This is known as PVT surface. So in general, the shape of this surface remains the same for most of the thermodynamic systems. Remember that. So, and this green region. Now what does that mean, green region? Just look at this one. This is one green region, because this green region is it is basically defining a region at the boundary of solid and liquid. It means within that green region, for all the pressure values and temperature values, let's say all the combination of these three properties, you would see that you would have both solid and liquid. Just like that. For example, you might be considering melting of an ice cube. What is that? This is basically solid, and a few amount of solid has been converted into liquid. So it means on this set of, if I just calculate pressure and temperature and specific volume at some point, I would say that on this point I would have both ice and water in liquid state. Now let's talk about this one. Now I am specifically writing solid, liquid and vapor over there because I know that, but in the next figure I would show you some actual figures related to different substances, and you would understand why I am writing it like this. So this is something in this region. You would have on this left side you would have liquid, and on this right side you would have vapor. So you would say that in this region you would have liquid vapor region, right? So this is liquid vapor region. So liquid vapor region means you may look at the boiling of water. You would have some vapors coming out of the surface, and then you have some liquid. So on all the points, on all these points within this region, you would have a small amount of vapor and small amount of liquid, right? So this is my objective. Then just look at this point. This would contain something like solid vapor region. This is again a green region. I would specifically define these things, but just to give you an introduction, I am defining it like this. So what does that mean, solid vapor region? I hope you understand the word sublimation, right? So what does that mean? That straight away from the solid state, material goes out like the vapors, as if they are vapors. So this is something which is known as sublimation. So if you want to have sublimation, you need to have this combination of pressure, specific volume and temperature. If you want to have sublimation, do you understand that? Now you have a question. Have I defined it like this? still I have not defined it. There are so many other points, so just wait for a while. It is what? Can there be what? You can say that. You can say that. No. Generally, or for most of the cases, there are two properties. But there can be situations where you only have one property. There can be situations. Or there can be a situation where but I think generally you need to define two properties at least. Generally, either it is pressure or temperature, either it is pressure or specific volume, or in some situations you only can define pressure, you can't define temperature. So it depends on the behavior of the systems. It depends on the equipment which you have, what kind of sensor you can have in a particular situation. So there are some practical issues as well. So why it is like that? I mean, it is very hard to define it, why the system behaves like that, but the point is, you just somehow or the other, by doing experiments, you somehow or the other define the response, that this is how it is going to behave. I may not be able to answer. I think it is very hard to tell you that why does it happen that sometimes pressure does not become a function of temperature, or temperature does not become a function of pressure. It all depends on the state of the system or inherent chemical composition, but this is what I can say at this point. Okay. Any other question? I think you have a question. What is an isotherm? All the points where you have same temperature, if you connect those points, that line would be defined an isotherm. Just like that. For example, if you look at the region, for example, just look at those points. If I connect all those points, it would give me the blue line. And what is the similarity between all those points? It is having the same temperature. Similarly, if you look at those red lines, it is doing what? It is giving me the same pressure value at all the points. If I connect all the points, it is what? It is an isobar. You have a question? What? No. It means if you look at the combination, by the way, if you look at the combination just like that, for example, now what is the state? The state is being defined by what? Right? So it means I can fix this specific volume and temperature, and then I would be able to find out. But what does that mean? At this specific state, system is in equilibrium. What does that mean? That without doing something externally, you can't change the state. If you want to jump onto the next point, you have to do some work. You have to provide some energy. Okay. So now this is quite interesting. I mean, generally those shapes are defined, and if you look at the left figure, this one, this is for a substance that contracts on freezing. Most of the substances contracts on freezing. Most of the substances. Okay, you talk about any substance except water, which expands on freezing. Now there is just one difference. There is just one difference. If you look at solid liquid region, it slopes like this. In the case where substances contract on freezing. But if you look at those substances that expands on freezing, you would see that it is going other way. This is the only difference you can say. Okay. In one case, solid liquid region is sloped like this. In the other case, it is sloped like this. Right. So this is the difference. Remember that. Now, I would define few things. I hope you understood that these solid, liquid and vapors, these are single phase regions. These are known as single phase regions inside that PVT surface. Okay. Now remember that even within the solids, you can have different chemical, not the chemical composition, but you can have different phases even within the solid. Now what does that mean? That for example you may have different crystalline structures. Do you remember how many crystalline structures for carbon there are? I hope you understand that, graphite or what, diamond and all other things. So within that solid region there would be something. So just look at that. Even within that solid region you may have different crystalline structures. Like for example, I think there was a mention in this book that there are 17 crystalline structures for water have been discovered. 17 crystalline structures. So within that solid region you may define the regions for those certain specific crystalline structures. Okay. Now those crystalline structures, I think you would be able to define it in your materials course. I don't remember the exact name of that phase diagram, but I think they call it like fish diagram. It just looks like a fish. Okay. So if you go to your materials course, you would see that there, or I think manufacturing course, they would discuss that fish diagram where they would discuss different kind of phases. So anyways, so those solids are there, liquids are there, and then you have some vapors. Yes, it is counted as one phase, right? It is, at one time it would have, I think, one crystalline structure at one time. But my point is just to tell you that even within that region you have certain different things. Okay. So the point is you have three single phase regions. Single phase regions are three. Then you have solid liquid region, which is basically the slope of which is distinguishing those two types of substances that contract on freezing and that expand on freezing. Then you have solid vapor region, and within this region, this dome like shape, you can say that you have liquid vapor region. Okay. So no, it is only the behavior of the system. I would tell you, just hold on. Let me explain few things first, and then I would. Sorry? Where is the solid liquid state? Here? This one. This region. This sloped region. This slanting region is basically defining what? Solid liquid region. Yes, it's on the back side. Okay. No, these are not different phases. Phase is solid. You have inside them you have crystalline structures. No, they are not minute. By the way, we are not interested in thermodynamics. You can be interested in those crystalline structures once you talk about material subject. Okay, I am not interested in discussing that. Yeah, I mean, I'm just telling you these things so that you can connect all those subjects, and sometimes you get a good perspective if you look at it from another subject's point of view. Okay, so that's why I'm telling you this thing. Now, all these three regions, you have three two-phase regions. Okay, you have three two-phase regions. Now, just look at this line. I'm talking about this line, this red line, or this line. Along this line, along these two lines, you can say that all the three phases would coexist. All the three phases would coexist. It means that if you look at temperature, pressure and specific volume values, if you have got a certain set which comes onto those lines, this line or this line, you would say that all the three phases coexist, and this line is known as triple line. This line is known as triple line. Okay. Sorry? No, coexisting mean, for example, you have some vapors coming out of that solid part. You may have some ice. The ice is melting as well. So all the three phases are coexisting. Coexisting means they are existing simultaneously, just like that. For example, if you have a cube of water there, you would see some vapors are coming out of it. There would be some solid structure, and then there would be some liquid region as well. So they are at a boundary of solid, liquid. I mean, this is basically having both liquid and vapor. This is having solid and vapor, right? So along this line, you can have all the three regions, all the three phases coexisting, right? Where is that region? You are talking about this one? No, I'm just talking about. Remember one thing. These curves have not been derived from, let's say, or this surface, the shape of this surface have been derived from experiments. Remember that. This is not coming from some fundamental principle that according to energy or according to first law, second law, or Newton's law, this shape is like this. No. I mean, this is something which has come out of experiments. So experiments have shown that along this line you have all the three phases coexisting. Similarly, if you look at this line, you would have what? Triple line, right? So remember that triple line is just a line there. Now, within this dome shape, which is known as vapor's dome, this is known as vapor dome. This dome shape, this is known as vapor dome, and within that region, you would have what? Liquid and vapor. So this is something which is what? Vapor dome. And if you say that you are lying inside the vapor dome, what does that mean? That some mass would have been converted into liquid and some mass would have been converted into vapor, right? So this is something. And remember that we would define a specific property related to this region. Specific property, okay? So now I hope you at least understand what are the regions, how do they look like, and what are the two-phase regions, what are the single-phase regions, what is a triple line. Then just look at that. Now vapor dome region means that inside that dome, for all the properties, for all the states, you have what? Both liquid and vapors coexist, right? That is why, because it shapes like dome, so that is why it is just known as vapor dome, right? Now there is just one point left related to this figure. You can see this critical point. Now this critical point, you can see this is the maximum temperature. This is the maximum temperature where you can have both liquid and vapor states coexisting. This is the maximum temperature, right? So temperature at this critical point is known as critical temperature, and the pressure line passing through that critical point, that would be known as critical pressure. Okay, so I hope you understand the word critical point. Critical point, this is defining the temperature, which is what? Where this is the maximum temperature where liquids and vapors can coexist. Okay, so no, there is actually a specific boundary on that surface. Yes, exactly. I mean, all those, like for example, just to answer your question or to further my discussion, if you look at this line, this is the line where you can have complete liquid. This is the line, and on this side of this line you would have complete liquid. On this side you would have some liquid converting into vapors. So this line is known as saturated liquid line. This line is known as saturated liquid line. Similarly, on this side, there would be, on this side you would have liquid plus vapor, but on the other side you would have only vapors. So this line is known as saturated vapor line. Okay, you can see those two lines. On the liquid side you have what? Saturated liquid line. On this side you have saturated vapor line, and the point where those two lines connect, there is another definition. That point is what? Critical point. That is the maximum point, that is the maximum temperature which you can have where both the liquids and vapors can coexist. I hope you understand that. Any question? Sorry, there is what? No, the constant pressure lines would be passing through that surface. No problem at all. They would be passing through that surface. Okay? Yeah. But there would be a line which is passing through that critical point as well. Why? Because that critical point would have some pressure. That critical point would have some pressure. It would have some specific volume. It would have some temperature. So all the points which have the same critical pressure, which have the same pressure value, if you connect them, that would define an isobar. Right? What you are talking about, this line? No, if you are talking about this line, this should be what? This should be an isotherm. If you talk about this line, this is what? A constant pressure line. Just look at that. The isobar, sorry. This is something which is an isobar, which defines a specific value of pressure. So along this whole line you have same pressure. So this is an isobar. If along some line you have same temperature, it is an isotherm. No. This is the maximum temperature where those two states can coexist. Solid liquid what? It can be having a. No. I mean, in this case, this boundary lies along this line. It is not lying on a point, right? So that is why it is a critical point.
So it can be called as a boiling point.
No. I would discuss that boiling point as well.
So what do you call the pressure line going through the critical point?
I mean, if you look at this pressure value, it would have certain pressure P1, for example. There would be some other point which would have that P1 as well. There are so many points on this surface. If you connect all those points, let's say along this surface, this could be an critical pressure line, or you can say this is an isobar. That's what it means. Okay. Yeah, I mean, then in that case, by the way, there is a certain point from the practical point of view. I am talking about from the practical perspective, in the real application, applied sense. Applied sense says that there is a point where this discussion becomes meaningless, whether the system is in liquid state or is in vapor state. So there are some points. We generally don't go beyond that. But to define this surface, what you can see is that beyond that pressure line, if you talk about this is the critical temperature line, this line. So beyond this line, on this side, you would have liquid, and on this side you would have vapors. Just to understand it. Okay. So this is something just to answer your question. So any other thing related to this figure? Between what?
This is small wedge between the solid vapor and the liquid vapor.
You are talking about this thing?
Yes.
Yeah, I mean, still it is defining what? A solid vapor region.
And what I want to understand that how can you understand the general trend, like as the temperature is increasing?
I mean, you can't be saying that this is a general trend. Remember that. That's why I'm spending so much time on this figure. You can't say that in every case this temperature would be increasing, this pressure would be increasing, this specific volume would be increasing. No. In every region you would see that there is a different behavior. In every region. Okay? And that's why I'm trying to explain all those behaviors, or at least most of them. So any other thing which you want to ask about this point?
So that's solid liquid flow.
Okay, you talk about that solid liquids. Okay, you talk about that slope. Okay, just look at that. If you have a certain temperature, you would have a certain pressure value and you would have a certain specific volume value, isn't it? Now, just see that if you increase the temperature and specific volume, you increase the temperature and specific volume. By the way, you don't have to look at the specific volume, but just think that in this case, if you increase the temperature, pressure increases. Do you understand that? Come on to this one. If you increase temperature, pressure decreases. Why it is going like this? If you look at in the direction of the temperature increase, if you increase the temperature, which is increase in temperature here, just see, this is one point, this is T1 and this is T2. Obviously T2 is tilting on the right side. So if T2 is tilting on the right side, you are increasing temperature but pressure is decreasing. In this case, what does that happen? What happens? If you increase temperature, pressure also increases. So that is something, how do you establish equilibrium, or how do you look at the states for different types of materials? Generally these are the two shapes, and in a broader perspective they look like same to each other, isn't it? They are similar. No, that graph is not designed. That is something which you have got from experiments. Okay, remember that. Whenever you talk about design, it means you have done something by yourself. You haven't done something by yourself. This is something which you have got from experiments. That's how system behaves. No, only two variables. Only two variables. Okay, any other question? Now, this is a broader perspective for PVD surface. At least you know that, right? Now, the point is, if you want to use that surface for problem solving, like you are trying to design a system, how would you use that surface? So most of the time we use those surfaces in the forms of the projections. We don't use this surface as if it is a 3D surface most of the time, because those projections are quite helpful, and we are basically generally we are familiar to 2D plots, so that's why we always look at those things in those terms. Now just look at this region. Here, if you just look at this surface from a side, so it would look like this projection. Just see that. And this projection is known as PT surface. PT surface means, just think of your engineering drawing course and look at this view. What does happen? Just look at this view, this side. I mean, just think, this is the surface and you have aligned it according to what? You are looking from the temperature side. Okay, so this is something which is known as PT surface. This is something which is known as PT not surface, PT projection, and this is the something which is known as phase diagram as well. Generally, this PT projection is known as phase diagram. Okay, so in this case, you can see that all the two phase regions, they have come as their lines. All the two phase, think of it. This was, which of these regions? This was solid liquid region. So this has become a line. Similarly, this was what? Solid vapor region. So this has become a line again. This was what? That was the dome-like structure, right? So pressure increases. Okay, then what? Okay, that was described as the difference between two plots. He asked me a question, what's the difference in those two slopes? How can we see it? So my point was, the difference is in one type of material, if you increase temperature, you would have an increase in pressure. In the other material, for the other substance, if you increase temperature, there would be a decrease in pressure. So that was the difference in slope. I was describing that. No, this is just a schematic thing, just to make you understand. You can't say that. You are ignoring the fact. You are just trying to make the things easier for you. You are just trying to simplify the things. Okay. So the point is, you just look at this plot. This is also known as phase region, and you can see your triple point has also been converted into what? Triple line. The triple line has converted into what? A point, right? So remember that was the point which was known as triple point, and I used that point to define what in chapter 1. I told you that for Kelvin temperature you define what? Triple point as the reference, right? So this is the point which we talked about, triple point. Okay, this is something on the phase diagram, and you say that this triple point has been agreed upon by the world that we would give this triple point a value of temperature as just like 273.016 Kelvin. This has agreed because you need to set certain references, isn't it? Certain standards. So you have to define where does your zero lies. So I mean, this is something which was taken as the reference. So this is something which was taken as something which can give you a reference point to define the Kelvin scale. Okay. So you can say this is known as triple point, this point. And this was shown as triple line in the previous slide. And what does that mean, triple point? I hope you understand the definition. You remember the definition where all the three phases coexist. Okay. Exactly. I mean, this is the importance of reduction of the parametric space. If you reduce the parametric space, it becomes very easy. And the only thing, or the only point for that reduction is you need to see how those properties are interdependent on each other. What happens if there is a point on the? Oh, there can be no point on the gray region. Remember that. There can be no point on the gray region. Why? Because if you just look at the dependence of pressure on V and T, specific volume and temperature, you would see this is how surface goes, just like that. Can you have any point on this region? No, you can't have that. I mean, your surface is going like this. Like for example, if you just plot pressure and temperature and it is going like this, if I ask you what is the value of pressure on temperature, would you say it is there? Obviously you would look at the surface. You would look at the surface. So this gray region is something which is out of that surface. We are not interested in that. Okay. So I hope you understand that, how we look at the projection. So this is something which is known as phase diagram. So let me see a few points so that I can explain that. So for the next figure, how many views can be there? How many orthogonal views can be there? 3. So we would look at all those 3. Okay. So just look at that. I mean, these are the 2 plots which we were talking about. This is for a substance that contracts on freezing, and that was for a substance for expands on freezing. Just look at that slope. This is the slope. Okay. So just to answer your question once again, I think you asked that question. Beyond this point, I mean, this is the temperature. So this is the critical temperature. So within this region you would have what? And in this region you would have what? Liquid. Okay. So similarly, the same things happens over there. So just keep your eyes very familiar with those figures, right? Okay, let's talk about the PV projection. I hope you understand. On the vertical axis we would have P, on this side we have V. Just look at that. So what are the where are the isobars? What are the colors of the isobars? Red line. And you can see that the pressure value remains the same. Specific volume can change. Now similarly, if I ask you, what about this isotherm? Let's say, just look at this isotherm. On this isotherm, you would have critical point, you would have critical temperature. So all the temperatures, or all the isotherms, all the constant temperature lines or isotherms which are lesser than critical temperature, they are passing through this dome. They are passing through this dome. Now similarly, for all the temperatures greater than critical temperature, you would not be able to pass through that dome. It means you won't be having liquids and vapors coexisting. You won't be having liquids and vapors coexisting. Remember that. Okay. So So I have told you all the relevant important points.
Can you repeat again what
Just look at that. You can see that how does it look like for all the two. I'm also showing you the projections of those two figures for those two types of substances, contracts on freezing and expands on freezing. Okay, just look at that. For specific volume and for specific within that liquid vapor region beyond this triple line, you can see that there are certain points where this pressure remains the same. Where this pressure remains the same. And just think of it that, for example, if you look at this region, I am just talking about this region. This is the solid liquid region, so this would be liquid region. Just look at that. Beyond this point, you can see that a small increase or decrease in specific volume can affect the pressure to a great extent. Just look at that. This is what is its slope? It is straight away coming down. So if there is a small decrease in specific volume, small increase in specific volume, if there is small increase in specific volume, what you would see? A sharp decrement in pressure, right? But if you come to this region, which is basically maybe the vapor regions, what you can see that the pressure decrement the rate of that pressure decrement would decrease. It would decrease, but not to that extent what was happening over there. Okay, so there are few points related to this thing. I have already told you what would happen for T lesser than T critical, what would happen if you have T greater than T critical. Any question? No? Understood? Okay. Where is what? Solid liquid phase in second diagram. By the way, can you look at this dashed line? What does that describe? It is something on the other side, which is something known as hidden line in your engineering drawing course. Okay. So it might have been overlapped by one of these two lines. By the way, these all figures are not drawn on some scale. These are not scaled figures. These are just the representation of all those surfaces. Okay. So this is something which is known as TV projection. You can see that you are looking at that surface from the top, and that's how it looks like. And more appropriately for those two figures, this one. Just look at that. This is TV projection, and this is a representative for water. This is representative figure for water. Okay. Now be very careful and look at this thing very carefully. For example, you start from this point. This is state 1, and this temperature is basically 20 degrees centigrade, which is basically 68 degree Fahrenheit. I would just be considering that degree centigrade. So this one point is basically 20 degrees centigrade, and what you are doing is this: you have a liquid water, liquid state, complete liquid state, right? Now this line is what? This line is known as what? Saturated liquid line. This line is known as what? Saturated vapor line. This point is something which is known as critical point. Now, if you go beyond that, situation becomes meaningless, right? But for the sake of understanding, what we can have is, beyond this critical point we would have all vapor state. beyond this point. Now, if you start heating that system, just look at that figure, liquid water. If you start heating that system and you keep the pressure constant, now the pressure remains the same, but you are heating the system. This is the situation. Now, as a result, this piston would start moving up. Why? Because obviously the system is getting some kind of energy, and if that energy is being converted into work, which the gas is doing on piston, obviously that pressure would remain the same, right? So you can say from here to here, going from here to here, you would have complete liquid region, and your pressure remains the same. Remember that your pressure remains the same. You are going on this isobar. You are going on this isobar. If your pressure changes, it means you have jumped on to the next isobar, isn't it? Do you understand that? Now,
But there are two pressures, one which is being exerted on the piston and the other on the pressure of the gas.
I'm talking about pressure of the gas, because that pressure of the gas is basically a result of what? The atmospheric pressure plus the pressure which is exerted by the weight of the piston. I'm talking about pressure of the gas.
Also, if the piston moves upwards, so shouldn't the pressure increase?
Why is it so?
For increase, and the volume will increase.
No, that volume would increase. But for example, if you basically keep your piston moving in the upper direction, so it means pressure remains the same, because you are providing some kind of energy to the system. That energy is being converted into some work. Remember that. That energy is being converted into some work. Okay, and what does that work is? That is P into V1 minus V2. Remember that. Okay, so the point is that if you start heating that start heating that system, after some point you would come on to this F point. And this is something where your vapor region would start developing. Okay, your vapor region would start developing. And once you are on this point, you would see that if you still keep your system heated, if you still keep heating the system, you would move along this line. What does that mean? Your temperature remains the same. You might have heard about this thing. During boiling, your temperature remains the same until you convert all the liquid into vapors. Do you understand that? So this is something which you do by your pressure cooker. When you put the lid on your vessel where you are heating that liquid, what you are trying to do? You try to increase the pressure, right? Now there is a very interesting point out of this figure. Now just let me explain this point first, and then I would tell you one of the application which you might have seen on hilly areas. Just look at that line. On that line, specific volume increases. Now what does that mean? If specific volume increases, what happens to the density? Density decreases. Remember that. So you can just relate those two things. So the point is, if you keep heating the system, you would reach that G point. And this G point is what? It defines the complete saturated vapor state. Okay. Now, once you convert all the liquid into vapors, once you completely convert all the liquid into vapors, a small change in specific volume would have a large change in temperature. And this is something, this region beyond this saturated vapor line, this is something which is known as superheated vapor state. This is something which is known as superheated vapor state. And whenever you talk about superheated steam, you might have heard about this word, superheated steam. What does that mean? You are lying in this region. You are lying on the right side of what? Saturated vapor line. Understood? Yes, along this line pressure remains the same. Now if you change the pressure, remember that. Now let me come to that point which I wanted to discuss. If you change the pressure, for example, you move on to lower pressure region. You move on to lower pressure region. What would happen? Would that boiling point be reduced, or be it increased? It would be reduced. Remember that? So for example, if I talk about somewhere here, this would be another isobar which may be having lesser value of pressure. So this is kind of the boiling point for that pressure. Is it reduced or increased? This was the boiling point at higher pressure. This was the boiling point at lower pressure. So it would what? Temperature is decreased. So if water boils at 100 degrees centigrade in Pindi, it may be boiling at, let's say, 98 degrees centigrade in Murray. Do you understand that? So that's how you can just look at that figure and see what would be the boiling point, what would be the sublimation point, what would be the saturated vapor point, and all that. I'm sorry, where is that? This is point 1, this is F, and that was G. So you are talking about which point? Yeah, this is something which is being defined within this region. Yes, this is inside the vapor dome. This is inside the vapor dome. All these states are inside the vapor dome. Yeah, this one. G and beyond that, everything is related to this one. Right? It is the constant pressure line all along this one. Beyond that is again a constant pressure line. You don't change the pressure. You don't change the pressure. If you put the lid on that, what does that mean? Think of it. Okay, any other question? Sorry? Okay. To pass it from the critical point, you have to go on to the specific isobar. Remember that. You have to go on to the specific isobar. If your isobar is at this value, 22.09 megapascal, then you would be passing through that critical point. Otherwise, you won't be passing through that critical point. Do you understand that? So just look at this thing and keep in your mind that you are working in, let's say, some power plant, and you are trying to guess the value of, let's say, pressure, temperature, or specific volume of a steam, superheated steam. So can you please tell me in what region would you be lying? Beyond this saturated vapor. If you are basically having some kind of liquid, you would be having what? On this side. And if you have some combination of both, you would have what? Liquid vapor region. Yeah, it is something which is superheated vapor state, superheated steam. Okay. Yeah, exactly. You would be jumping on to different isobars, right? And remember that you have to jump onto the isobar according to the surface. Remember that. You won't be somewhere staying here, let's say. It won't be like this. If this point is not on that surface, PVT surface, it means it is physically impossible to have this point. Right? So you need to have that point physically occurring on that PVT surface. Just like the gray region, the example of that gray region. That was physically you don't have that gray region. Okay? So any other point? This is the saturated vapor line. This is the saturated vapor point, and beyond that you would have superheated. Do you understand that? Any question about those figures? Because it is very important to understand in what region do you lie. Because if you understand this thing, then you would be able to use those thermodynamic tables which we are going to talk about. If you have any question, you can ask me. Now, by the way, just to define it, this region, this liquid region is also known as subcooled liquid region. I am just going to tell you a few names about these regions. Subcooled liquid region, You can also call that region as compressed liquid region. By the way, these are the names used in the literature. In different books, you would see those names: compressed liquid region. And I've already told you that this is something which you can call it like superheated vapor state. Okay, beyond that saturated vapor line. Now, there comes the question. There should be a quantity which may tell us how much liquid has been converted into vapor, isn't it? That, for example, if I am at this point on this line, I should be knowing what percentage of liquid has been converted into vapors. I should be knowing it, isn't it? Now, that quantity which defines this thing, how much liquid has been converted into vapors, that quantity is known as quality. That quantity is known as quality.
Are you going to compare this percentage for one level?
Sorry? Just hold on. Can you please let me this finish first, and then I would come back to you. So this is something which is known as quality, and this property defines how much liquid has been converted into vapors. Okay, and this quality is generally defined by X. Remember that we would use this letter to define quality, and this is known as mass of vapors over mass of liquid plus mass of vapors. So that's how you define quality. Sorry? It is specifically for what? No, for the vapor dome. If you lie within that vapor dome, obviously you need to know what percentage of liquid has been converted into vapors. Okay, so that quantity which defines this thing, that is known as quality. Right? And this quality is only defined within that vapor dome. Okay, because within that vapor dome you can have those two phases coexisting. Okay, any other thing? Right. So these are different perspectives. Just look at that PT diagram. Generally we call that as phase diagram. I hope you remember that. If I talk about phase diagram, it means I am talking about PT projection, pressure temperature projection. Now here you have this triple point. Here you would have this triple point. All these lines are defined two phase regions. Now beyond this point, you would have what? Sublimation. Remember that this line was defining what? Solid vapor region. Beyond this point you would have vapors. Then just look at that. This is something which was defining solid liquid region. So it was defining a phenomena melting. Okay, so on this side you would have solid, on this side you would have, this is the only point where you would have all the three phases coexisting. Then if you go on this line, this is something which is known as vaporization or condensation. Now there is something, because if you convert vapors into liquid, that is something which is known as condensation, right? So this is the reverse process of vaporization. So on this side you would have liquid, on this side you would have vapors. Now the point is, if you look at this critical point, that is the critical point which a substance can have this maximum temperature where you can what? All the liquid and vapors coexist, right? So on this line you would have liquid, and on this line you would have vapors, right? So any question about that?
So you just said that this is going to all the liquid and vapor coexist.
This is the maximum temperature where those two states can coexist. This is the maximum temperature, right? That's the point. Now the point is, I would go back to this one. You are talking about this point? I mean, if you go on this line, you keep increasing the temperature, it means you are vaporizing. If you are going reverse, it means you are doing what? Because there is a pressure coming up. There is a role of the pressure. Yes, there is a role of the pressure. Right? You can't negate the role of the pressure. Remember that. Okay? So, no, I mean you can't do it like this. If I accurately understand your question, I think you are talking about something about the process. That if you go on this line and you have vaporized all the states, would you come back onto the same line if you want to condense the liquid? I don't think, because most of the time in nature you have a process known as hysteresis. Ideally we can say that. Yes, you can say that. I think so. I think so. You can say that. Or you can say that you would have a very small region of hysteresis at that place. I think so. I hope you understand what hysteresis is. Right? You come back onto this path. If you go back to the same point, would you have the same region or not? Right? So there would be something like different. So anyways, so this was something which is known as liquid. So gentlemen, the same kind of explanation what we have seen for this solid water, and then it has been converted into vapors, and then it has converted into the complete vapors, and I have shown you how you go on these lines, on these pressure lines. You can also see how sublimation happens, how sublimation occurs from solid state to vapor state. You can also see that. There is a paragraph in your book, you can just take it as a reading assignment. So the same kind of description, no problem at all. How do you go along the isobars? How do you go along the isotherms? I mean, this is something which you need to understand. I have tried to explain it. If you have any other question, you can still ask. Okay. So the point is, this is very interesting again. Okay. Some question? So, gentlemen, we have some tables which show these properties in terms of their values along that PVT surface. We are going to use those tables. Okay. Now, I would show you this table. I have taken it from the book of, I'm sorry for that name, this is Moran and Shapiro. So, what you can see is, this is the properties of superheated water vapor. These are the properties. By the way, you can have different tables for different regimes of different materials. You can have that. In your books, in your reference books, you can find those tables for those materials which are commonly seen in thermodynamic application, just like water. Most of the time we would be using water, or we may be using ammonia, right? So these are the materials with which we would be generally dealing. Just look at those properties. This is properties of superheated water vapor. I hope by just looking at that phrase, this should have come into your mind in which region you are lying. Do you understand that? Now the point is, if I give you a certain pressure value for this region, what would be the starting temperature? What would you call that temperature, starting temperature? Wouldn't that be the saturation temperature for the vapor states? Because you are lying on what? Saturated line. So you are exactly lying on saturated vapor line. So you can see that those tables would start from what? Sat. It means saturated. And what is that saturated temperature? This is 36.16 degrees centigrade. Okay, so for this pressure, if you have this pressure, you would have this saturation temperature, and this saturation temperature is 36.16, and then you start increasing. So for example, if I ask you that in some thermodynamic system you have a pressure of 0.06 bar, and just tell me the value of the specific volume at the saturation temperature, you would come onto this table and you would straight away tell me that it is equal to 23.739. Do you understand that? Okay. My point is, I hope by just looking at that phrase superheated water vapor, let me make it bigger. Yes, this one. I hope it is visible to all. Just look at that. This is properties of superheated water vapor. So similar kind of headings you would see on all the tables. Superheated, subcooled, compressible, all these things are there. And by just looking at that phrase, you should be able to understand in what region your system is lying. Okay. And then just look at that superheated vapor state. It means that superheated vapor state is starting from which line? Saturated vapor line, right? So if you have this pressure 0.06 bar, you can also convert it into megapascal and all the rest of the units. Saturated temperature is what? 36.16 degrees centigrade. Now what does that mean? It is also giving you a value of the boiling point. It is also giving you a value of the boiling point at that certain pressure. You see? Right? So just see that at saturated pressure temperature you have specific volume like this one. Just forget about the other properties. We will talk about that later on. So specific volume is what? 23.739 meter cube per kg. If I ask you what is the value of, let's say, saturated temperature at a pressure of 0.35 bar, what is that? It is 4.526. Just see, the temperature scale is only there. This temperature column is only there. So all the things remain the same. Okay. So now there is a very interesting point. If I ask you, let me tell you this very quickly because we are short of time. If I ask you what is the value of specific volume at a temperature of 100 degrees centigrade, do you have any specification for 100 degrees centigrade over there? Not at all. Now, what would you do then? You have a value of 80 and then you would have a value of 120. So, like for example, if it is right in the middle of those two values, 100 is right in the middle of, you can take the average. But if it is, let's say, 95, then you would do interpolation. Then you would do what? Interpolation. Just like, for example, let me plot this figure for you. Let's say we have temperature on this side and we have specific volume on this side. I am just reversing the axis. Okay, I hope you understand that. Now this is the point for 80 degrees centigrade, let's say, and this is the point for, let's say, 120 degrees centigrade. Always show the axis label and units whenever you draw the plot. Remember that, right? Now, if I just join those 2 points by a line and I want to find out a value at 95 degrees centigrade, I am lying somewhere here. This kind of process is known as linear interpolation. Why it is known as a linear interpolation? Because I am trying to fit a line for all the data points between those two known points. These are the two known points. So I am trying to fit all the data points between those two known points by a line. So that is why it is known as a linear interpolation. If I draw a cubic line, I would say that it is cubic interpolation. If I am trying to draw something like a parabola between those 2 points, I would say it is a quadratic interpolation, right? So something like that. So you can see what is the difference between linear interpolation, and you would see these kind of things in your numerical analysis course. But the point is, if I want to have this value, can you tell me how can I find that out? I hope you, because this is the equation of a line, isn't it? Can I say that this is something y minus y1 would be equal to m into x minus x1? Can I say that? How can I find out that m? If it is, let's say, T2, and if it is T1, and similarly if it is V2 and if it is V1, I can say V2 minus V1 over T2 minus T1 into x minus. So you can take any, like this would be V1 then, and this would be T1 then. Okay, so for example, if I just give you the actual values, at this point you have 27.13 and 27.13 for the lower temperature, and then you would have 30.209. So what I can see is this would be y minus what? This y is something which is known as V, right? On the y axis I have V. So V minus V1, which is 27.13, equals 30.209 minus 27.13 over T2 minus T1, which is 120 minus 80, and then this should be equal to minus T minus what? X1 was 80. Okay, so now if I plug the value of 95 over there, I would get the value of V, right? So if you have a value right in the middle of those two given values, you can take the average, no problem at all. Why? Because you would be lying exactly in the middle, so it would be exactly the average, no problem at all. But if you are going somewhere here and there from the middle point, it means you have to go for the linear interpolation. Okay, so those were the points for today's lecture. We have seen how we can describe PVT surface, what are the important regions, lines and points, how you can associate those two regions with your practical situation of the system, and then how you can use those tables at least for two regions. I am just talking about one single phase regions. Remember that I am just talking about single phase regions. I have told you something about the vapor region. In the next class we would talk about something like the compressible liquids, and then we would also talk about the vapor dome as well. Okay.